Okay, guys, let's review real numbers and solving and justifying equations. Here's our first equation, and we're going to write it in our two-column proof, and the first statement is simply just your problem. And the reason for this is because it's our given. Now we're going to solve and find the value of x. So let's walk through what's happening. If we knew the value of x, so let's see how many operations we have. We have 1, 2, 3, 4. So if we knew the value of x, we would multiply by -2, then we would add 6, and then we would divide by 4, and then we would subtract 8. So now we're going to undo this and solve, so we're going to work backward, and we're going to add 8 to both sides. And when we add 8 to both sides, we end up with it equaling 18, and we use the addition property of equality. Now we need to undo the division, so we're going to multiply. Let me show you how I like to write this. So we're going to multiply both sides times 4, and that way the 4's cancel out, and we're left with -2x plus 6 equals, and what is this going to give us? That will be 4 times 8 is 32, and be 72. Okay, then we have to undo the addition. So we're going to subtract 6 from both sides. Oh, let's do this up here, sorry. Multiplication property of equality is what gave us that statement. And then here we did the subtraction property of equality. And now we're going to divide both sides by 2, or I should say -2, and that's going to give us -33. So we did the division property of equality. And we have exactly one solution. So the only value that if I plug in for x here, it would make the left side also equal the right side, which is 10. So only one value for our solution. Okay, our next problem, let's write it on our first line. And this is the given. And now the first thing we have to do to simplify an equation is if you have parentheses, we definitely have to dissolve the parentheses by applying the distributive property. And we get 4x minus 6 minus 2x. And don't be tempted to use another property on a line. Okay, so now we can collect like terms on the left and we can collect like terms on the right. So if you are using the same property, then that's fine. So combine like terms. And when I combine, that's going to give me 2x minus 6 on the left and 2x plus 12 on the right. Now, anytime that you have an equation where you have variables on both sides, you need to deal with the variables first. So typically we get rid of the smallest one, but these are the same. So we need to subtract them out, and the variables are eliminated, leaving us with this false statement. So this was the subtraction property of equality. And so there is no solution. There's no number that I could ever put in for x in all these spots that would make the left side equal the right side. So no solution. Okay, now we have the square root of 3x minus 9 equals -6. And this is the given. So if we knew what x was, we would multiply by 3. And then we would take the square root. And then we would subtract 9. So we're going to work backward and do the opposite inverse, or do the opposite operation, which is the inverse. So we're going to add 9 to both sides, so the addition property of equality. And this gives us the square root of 3x is equal to a positive 3. Now to undo taking the square root, you square it. So this is what this looks like. I'm going to square the left and I'm going to square the right. So squaring undoes square rooting. So I'm left with 3x is equal to 9. So that was the squaring property of equality. That's the action I took. Then we're going to divide both sides and get x equals 3. So the division property of equality. So we have exactly one solution. So if I plug in 3, I would say 3 times 3 is 9. The square root of 9 is 3, and 3 minus 9 does give us that negative 6, so it works. Okay, we have 2x squared plus 10 is equal to 4x squared minus 8. That is the given. We have variables on both sides, so we're going to subtract the smaller one. So I'm going to subtract 2x squared from both sides. And that was the subtraction property of equality. Now, x was being squared, then multiplied, then subtracted. So I'm going to undo the subtraction by adding. So the addition property of equality. And when I add, I get 18 is equal to 2x squared. Now we need to get rid of the 2 times, so I'm going to use the division property to get rid of 2 times. And I'm going to go ahead and switch this and put my x term on the left. Okay, and then we're going to take the square root. And remember, guys, when you take the square root, you're going to have 2 roots. So when I take the square root, it undoes squaring, leaving me with the x that we were looking for. And then I have either positive 3 and negative 3. So that was the square root property of equality. And I have exactly 2 solutions. Okay, the last part we're going to look at is which values are rational and why. So a rational number can be written as a ratio, and you can see the word ratio in our word, and a ratio looks like a fraction. Remember, you can never have a radical in your denominator. So let's go through these. So the square root of 12 is not a perfect square, so it would be a number that would go on and on without repeating and be a decimal that would continually go without repeating and not terminating, which means it would never end. So this is irrational. This is a perfect square and equals 12, and I could write it as a fraction. So this would be rational. And let me just change pen color so we can see this a little bit better. So anytime you can write a number as a ratio or a fraction, it is rational. This is already, so it's rational. This is a fraction, so it's rational. Pi is 3.14, but it goes forever without repeating and without terminating. So this is going to be irrational. 3.14 is a terminating decimal. It ends, so that's rational. This is a number that doesn't repeat and it doesn't end, it keeps going. So this is irrational. A repeating decimal, it is going to be rational. So if you just want to remember the word repeating starts with R and rational starts with R, because I could turn this into 8 and 12 over 99, just the little shortcut of how many of our digits are repeating. That's how many nines you use. And yes, we could simplify this, but I'm just showing that it is rational because I can write it as a fraction. On this expression, be careful because look, let's simplify it first. So the pi's go away, so I'm left with 2, and then I could put it over 1, so it is rational. The square root of 225 is a perfect square. It's 15, and then we have the negative out front, and then if we put it over 1 to make a fraction, it shows that it's rational. The square root of 50 is not perfect, and therefore it's going to be irrational. It's a number that would look like this. It would keep going forever without repeating and without terminating. This one is similar to the previous one, but look, both of these are radicands. So when I divide, I get the square root of what? 25, which is a perfect square, and then I can put that over 1. So that is rational. So I hope this video helps.